Hi, Assalamualaikum and a very good morning. So now we're going to do chapter 6, which is benzene and its derivative. We're going to focus on the subtopic of 6.3, which is chemical properties. So in this video, we're going to explain the electrophilic aromatic substitution of benzene, where it involves the reaction of halogenation, nitration, Friedel alkylation, and Friedel acylation. So all of these four processes here will be known as the electrophilic aromatic substitution type of the reaction. Okay, so here are the naming, and these are the types of the reaction, which is the electrophilic aromatic substitution. Also, after we have learned 1, 2, 3, 4, we have to explain and illustrate the mechanism for the EAS reaction, and we need to include the drawing of the resonance structure of the uranium ion. Also, for part C, we're going to explain the following reaction by the alkyl benzene produced from part 3, where it will undergo oxidation with the hot acidified KMnO4 as well as the dipotassium dichromate. It will also undergo halogenation, where it happens under the presence of UV, where it will undergo the free radical substitution, the similar one to the one in alkene. So without any further ado, let us start. So, benzene, unlike alkene, benzene tak seperti alkene, the benzene will not undergo addition reaction, for example, the addition reaction of bromine, and the benzene will not undergo oxidation. At the same time, it is very, very difficult for the benzene to undergo addition reaction. Okay, even though the benzene will have carbon-carbon double bond, however, they will not undergo addition, will not undergo oxidation, and even if they undergo hydrogenation, it will happen very slowly at high temperature and pressure. Why is that? This is because the stability of pi electron system will be lost if the benzene undergo addition reaction. Hence, what they're going to do instead is the benzene and its derivative will undergo substitution reaction, not the addition reaction. Okay. So for the electrophilic aromatic substitution, the benzene can undergo four important reaction. First, we're going to have the halogenation, where benzene going to react with halogen, for example, X2, which is general, reacting with the solvent of and the catalyst of FeX3 in order to produce the benzene with X. So from benzene here, it will form halobenzene, where one of the H here gonna be substituted or replaced by halogen, which is X. Okay, and X here refer to any of the halogen atom in group 17. So it can be Cl, or it can be Br, or so on. Let's say if I'm using Cl2 here, the acidic catalyst that I'm going to be using is FeCl3. So it needs to be consistent. If I'm using chlorine molecule, I'll be using the acidic catalyst of FeCl3, which is the Lewis acid here. Okay, if I'm using Br, then I'm going to be using FeBr3. Alright. At the same time, benzene can undergo nitration by reacting it with the nitric acid. So nitric acid going to have the formula of HNO3, or we can written it as HNO2 here. Okay, so HNO2 plus 1 here, so HNO3. So by reacting benzene with nitric acid, with the presence of acidic catalyst of the concentrated sulfuric acid at the temperature of 50 degree to 55 degrees Celsius, what we're going to do is we're going to substitute the hydrogen, okay, hydrogen with NO2. So the black color group here going to be substituted, and from benzene it's going to become nitrobenzene. All right. Now the benzene can also be reacting with the alkyl group here. So here refers to the alkyl halide, or RCl here can refers to haloalkane. Okay, so the Cl here can be changed into Br or can be changed into fluorine. It doesn't matter, because as long as it is an haloalkane. So when it is reacted with the presence of the Lewis acid of the LCl3 and this can also happens at arrangement, so you're going to look into that. You can see that one of the hydrogen of the benzene gonna be substituted with R. Okay, so R here refers to the alkyl group. So alkyl group can be CH3, can be CH2, CH3, and so on, as long as it has a carbon chain. Alright. At the same time, benzene can be reacting with the acyl group here. So this is known as the acyl chloride, and as what you can see here, the benzene, one of the hydrogen of the benzene gonna be substituted with the black color atom here, which is C double bond OR. So the benzene that you're gonna be producing is C double bond OR here. So from hydrogen, it's gonna be substituted into C double bond OR. So this need to be present with the Lewis acid, which is AlCl3, at the presence of heat. Okay, and at the same time, the alkyl benzene here, which the ones that you have produced, you will see that the alkyl benzene here, the R here, can undergo oxidation using KMnO4 and undergo free radical substitution under UV. So we're going to look into this reaction scheme in the later slide. Okay, as mentioned, for the electrophilic aromatic substitution, the H atom of the bromine, H atom of the benzene, gonna be replaced by the electrophile. So electrophile gonna be enter here, and the replacement of electrophile, where electrophile is inserted into the system, is known as the electrophilic aromatic substitution. So the mechanism will involve 3 steps, okay, which is first is the formation of the electrophile, second is the formation of the arenium ion or the carboxyl ion, and the step 3 is the deprotonation of the arenium ion. So now let us look into the halogenation first. So for halogenation, we're going to have the reactant of benzene and the halogen. Also, we need to have the condition here where it need to be with the presence of catalyst. So the example of the catalyst that we can use is the Lewis acid, which is FeCl3 or FeBr3. So if benzene is reacted with bromine without the catalyst, there will be no changes of the reaction. So it will stay as benzene. Okay? And that is why we need to write FeBr3 in order to initiate the chemical reaction. So this is compulsory. And as mentioned, when we are using Br2, we have to use Br here as well. So one of the hydrogen here gonna be substituted with bromine. Okay, so from benzene, it's gonna be bromobenzene. Alright, so now let us look into the mechanism in order to produce this product from this reaction. Okay, and for the observation, you can see that the bromine, which is initially going to be red in color, reddish brown in color, but when it undergo electrophilic aromatic substitution with benzene, the reddish brown color gonna be decolorized. Okay, so now let us look into the mechanism. So as for the mechanism, we're gonna have 3 steps, which is step 1, step 2, and step 3. And these are the reaction scheme that I snapshot from the previous slide. So first, you're gonna form the electrophile first. Okay, and the electrophile that you are having is the bromine molecule. So the bromine gonna be reacting with FeBr3, where the bromine gonna have the lone pair. So one of the lone pair is used in order to attack the FeBr3, which is the Lewis acid. Okay, and this gonna produce the Br plus and FeBr3, where the negative charge is gonna be on the ferrum. Meanwhile, the bromine gonna have a positive charge. So the positive charge here can be obtained from the formal charge, where the bromine gonna have 7 valence electron, minus 1, 2, 3, 4, 5, 6. Okay, so it's gonna be plus 1. So that is why bromine will carry a plus 1 charge. Okay, so these are the similar steps as what you have learned in chapter 4 of semester 1, which is chemical bonding. Okay. So same goes to here, where ferrum usually needs 3 electron, but because it attaching with 4 bond, so 3 minus 4 gonna be -1. Right? Now we're gonna use the electrophile that we have created and write it again here. So the electrophile that we have created, where this is known as the activated complex, it's gonna be reacting with the benzene. So benzene here gonna be reacting as the nucleophile. So the carbon-carbon double bond will have a lot of electron. So it's gonna attack the bromine, and this gonna break the bond in between the bromine-bromine bond and passes the electron into the positively charged bromine. Hence, this is gonna create a bromine with a positive bromobenzene with a positively charged here. So the positive charge here, for example, the carbon here, because it have 4 valence electrons, so it's going to be minus with 3 bonding electron, so it's going to be having +1. So that is why it carries a positive charge here. Okay, so this basically the electron here can be delocalized, as you have learned in the introduction part. So I can bring the double bond to this side, and this gonna create a positive charge on this side. Okay, and at the same time I can also bring the double bond to this side. Okay, so this gonna create a positive charge on this side. Okay, because the electrons are keep on moving around the benzene ring. Okay, elektron sentiasa bergerak di dalam benzene ring tersebut. So the positive charge gonna be move around, and the structure here is known as the resonance structure. Okay, resonance structure, and these are the aranium ion or the carboxyl ion form for the benzene ring. Okay, and for step number 3, you can draw this one again into here, and then you can break the bond in between the Br and FeBr3 because this is obtained from the step 2 punya reaction. Okay, so you can break the bond here, and you can use the extra electron that given here in order to attack the hydrogen. Okay, so you're gonna break the bond of CH here and passes the extra electron into here in order to form a carbon-carbon double bond in order to complete the benzene. So as what you can see here, the bromine is now attached to the benzene. So from hydrogen here, it's going to be attached with the bromine. So it's going to become the bromobenzene, and HBr going to be produced. At the same time, our acidic catalyst here going to be forming again at the end of the reaction. So FeBr3 bertindak sebagai catalyst. So at the end of it, you will be also producing a catalyst. So as you know the meaning of catalyst, catalyst will speed up the rate of the reaction without itself being consumed. So maksudnya FeBr tadi tidak dikonsume, tapi dia hanya terpakai dalam equation tersebut. Alright, nice one. Now we move on into nitration. So for nitration, the reactant that we need is benzene, and we need the concentrated nitric acid as well as the concentrated H2SO4 as the acidic catalyst at the 50 degree to 55 degrees Celsius in order to form nitrobenzene. Okay, hydrogen here gonna be replaced with NO2. And for the observation for the product, you can see that it's going to be a nitro substituted compound, which is nitrobenzene, and the observation that you will get is yellow oil. So yellow oil compound refers to the nitrobenzene. Now we're going to do the mechanism for the formation of nitrobenzene here. So this reaction scheme is taken from the previous slide. So first, for the formation of electrophile, you can memorize this equation here, and the electrophile that you're gonna be producing is NO2 plus here. So the hydrogen from here gonna be passes to here, and they're gonna form HSO4 and H2O as the byproduct. But what's important is you know that the NO2 plus is an example of electrophile. So you're going to use this for the second step. Okay, and as for actually step 1 will have a lot more steps, but for matriculation level you can straight away use this equation here to show the formation of electrophile. Okay, so now we have the electrophile where the basically nitrogen here, if you were to draw the structure correctly, you will have a positive charge here. Okay, but for now I'm just going to use drawing it this way. And if you were to count the formal charge, it's going to be 5 because nitrogen going to have 5 valence electron minus 1, 2, 3, 4. So it's going to have plus 1 and therefore it's going to have a positive formal charge here. So the reaction of benzene, which is the nucleophile, will attack the electrophile. Nucleophile menyerang electrophile, and this causes the attachment of NO2 and formation of the arenium ion. Dan seperti slide sebelumnya, we're going to move our electron. So the electron going to move here, and when the electron is being moved from here, this side going to carry a positive charge. Okay, and now we're going to move the electron from this side pula. So we're going to insert it here, and as a result, here going to carry a positive charge, and the other material going to be maintained. And you're going to enclose it with a bracket and show that this is a resonance structure, and it refers to the arenium ion or the carbocation ion of benzene. Now we're going to do the deprotonation of the arenium ion, where you're going to use the HSO4 minus, where HSO4 minus you get it from the step number 1 here. So you will use it again for the step number 3. So the negative charge will attack the hydrogen, and the CH bond here going to broken down, and we're going to break it apart in order to neutralize the benzene, the carbocation ion of the benzene here. So what we're going to have is nitrobenzene with complete carbon-carbon double bond, where we have 3 double bond in the benzene ring, and H2SO4 going to be produced again, which is the catalyst. Alright. Now we're going to look into the Friedel alkylation. So for the Friedel alkylation, we're going to have the reactant, which is benzene, and we need our haloalkane, or the other name of haloalkane is alkyl halide. So you will learn more about haloalkane in the next chapter, which is chapter 7. Okay, so benzene gonna react with the haloalkane. So here is the example of the haloalkane here, with the presence of the Lewis acid, with the presence of heat, in order to produce isopropyl benzene. So if you were to expand this structure, you will basically get CHCl, and then you will have CH3, and then CH3 here. Okay, so what you're going to do is you're going to attach, you're going to substitute your H, and the Cl going to be the leaving group, and the carbon-carbon single bond going to be formed here, which is CH, CH3, and also CH3 here. And this is known as the isopropyl. Okay, so now let us look into the mechanism. Okay, so for the Friedel alkylation, as you know, as I drawn here, this is going to be the secondary haloalkane. Okay, because it is attached with chlorine, and then it have 1, 2. So 2 alkyl group, so it's going to be secondary haloalkane. Okay, halo come from the halogen, and alkane is still an alkane, but just attached with the halogen. So when it attached with 2 alkyl group, it's going to be secondary haloalkane. So this reaction is for secondary or tertiary alkyl halide or the haloalkane. So this structure here is, I draw it again here, which is carbon-carbon, which is CH3 to CHCl with a lone pair here. So the lone pair here going to be used to attack the AlCl3, which is the Lewis acid, and this is going to form the activation complex, or the activated complex, and this is going to again break the bond, where we're going to bring the lone pair into chlorine. So what we're going to get at the end is the electrophile here, where the C gonna have a positive charge, and because two electrons are transferred into chlorine, so it will not, the positive charge is neutralized, dah tak ada dah positive charge, and the Al minus will still maintain the negative charge here. Okay, so now kita dah form kita punya electrophile. Okay, step 1, formation of electrophile, dan electrophile kita dah terbentuk. So now for the benzene, it is acting as the nucleophile. So nucleophile will attack the electrophile, and this is gonna cause the attachment of the CH3 2, which is our isopropyl. And as usual, we're gonna draw the uranium ion as shown in the previous slide. So elektron tadi akan bergerak. So pergerakan elektron akan sentiasa berlaku, and this will cause the formation of positive charge on this side, because electrons are moving here and positive charge going to be left here. So now we're going to move the electron from this side to here, and this causes a positive charge to be left on this position. Okay, and we're going to close the bracket, and we're going to label the resonance structure as the uranium ion. Okay, so we're going to draw the structure again for the last part here into here, and then we're going to take our nucleophile, which is ALCL3. So from this one is obtained from the step number 1 here. Okay, so what we're going to do first is we're going to break the bond and give extra electron to the chlorine, and the extra electron of chlorine is now used in order to attack the hydrogen, and this is going to break this CH bond here, and this bond going to be inserted here. Okay, similar step as before. So you will get benzene attaching with the alkyl group, and this is going to produce HCl because H akan combine dengan chlorine, HCl, and ALCL3 will be formed again at the end of the reaction. So because it is acting as the catalyst. Okay, so this one is for secondary and tertiary alkyl halide ataupun haloalkane. Now we're going to look about the same process, which is the number 3, which is Friedel alkylation, but now for methyl or primary alkyl halide. So here are the example of methyl haloalkane. Okay, so it's going to be CH, H, HCl. Okay, so almost similar step, but it just differ at step number 1 here. Okay, so at this step, the chlorine, which has a double bond, which has a lone pair of the chlorine, going to be used in order to attack the Lewis acid, and this is going to form the activated complex here. Okay, this activated complex will be used in step number 2. If you look into the previous slide, okay, for secondary and tertiary alkyl halide, we're going to break it again. Tetapi dekat untuk primary dengan methyl, we are going to use the activated complex here. So we're not going to break it again because it is unstable for the methyl and primary alkyl halide to do so. So we're going to directly use the activated complex here in step number 2. Okay, so benzene going to react with the activated complex tadi tu. Okay, and it going to attack the CH3, and this going to break the bond in between CCl here and passes the electron into chlorine. And macam biasa, we're going to form the uranium ion, where we move the electrons around the benzene ring in order to show the resonance structure of the uranium ion, and this need to be enclosed with a bracket. Alright, and the hydrogen here gonna be eliminated by the AlCl4 that we have produced in the earlier step here. Okay, so when we break the bond here, we're going to have AlCl, we are going to have Cl, AlCl3, so we're going to use it again for step number 3 here. So we're going to break the bond in order to give extra electron to the chlorine, dan chlorine tadi akan digunakan untuk attack the hydrogen, and this bond here going to break apart and pass the electron to the positive charge here. So what we're going to have is benzene and methyl group going to be attaching here. So what we're going to produce is methyl benzene, Dan pasal dia attach alkyl group, the name gonna be Friedel ALKYLation because it's attaching with the alkyl group. Alright, and this step here is for methyl and primary alkyl halide. For previous slide, okay, it's gonna have the extra step, and this shows for secondary and tertiary alkyl halide. Alright. Now, for the Friedel alkylation, masih dekat alkyl group, rearrangement may occur, especially when the primary haloalkane are used. Okay, let's say if you have a chlorobutane here, so 1, 2, 3, 4, 4 carbon, so it's gonna be chlorobutane in the presence of the Lewis acid. So at first you will suspect the product to be having CH2, 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 and CH3. Okay, however, this is gonna be the minor product. What really happened was you can rearrange the carbocation in order to form a much more stable product, which is the sec-butyl benzene. Okay, so this is going to be the major product. So rearrangement has basically happened, yang mana kita akan pindahkan hydrogen bila kita break the bond in between the Cl. So here going to get the positive charge. However, we can bring the hydrogen to this side in order to make sure that our positive charge to be more stable. Okay, so at first they are the primary carbocation, but when we transfer our hydrogen to here, this is known as the 1,2 hydride shift, and this is going to produce a secondary carbocation which is much more stable, and that is why product tadi tu, which is the sec-butyl benzene, gonna be the major product because the benzene gonna attach to this carbon instead of this carbon. Okay. Now we're gonna look into the fourth step, which is the Friedel acylation. Okay, tadi alkylation, sekarang acylation. So for this step, we're gonna get the reactant as benzene and the acyl chloride, as well as we need the catalyst, which is Lewis acid dan juga heat. Okay, so acyl chloride is C double bond O attaching with the chlorine here. Okay, acyl chloride, C double bond O with a chlorine. So this is known as the acyl chloride. And what gonna happen here is that the blue color here gonna be attached, gonna be substituted with the hydrogen here, and C double bond O CH3 gonna be attached. So from benzene, a ketone is now formed. C double bond O attached with C and C. So from benzene, it's gonna be reacting with acetyl chloride, which is example of acyl chloride, and reacting under Lewis acid to form acetophenol. Okay, so sekarang we're gonna look into the mechanism for the reaction here. Okay, similar step as before. Step 1, 2, 3 masih sama. So first, we're gonna form the electrophile. So the RC double bond O. So R ini boleh jadi apa-apa alkyl group. So let's say if my R here in this situation, R itu adalah H3C ataupun methyl group. So I can change it to CH3. Okay, tak jadi masalah because R can be any carbon chain. Okay, R can be any carbon chain. Tak jadi masalah pun. Kalau panjang, then you draw it longer lah. Alright. So now the lone pair of Cl gonna be used to attack the Lewis acid, and this gonna form RC double bond O and Cl plus as well as attached with AlCl3 minus. So this is gonna break the bond in between RC double bond O and CCl here in order to produce RC plus double bond O and AlCl3, where Al gonna carry a negative charge and the carbon gonna be carry a positive charge. Sama macam before, the formal charge of carbon gonna be 4 because carbon need 4 electrons, right, in the valence electron, minus 1, 2, 3. Okay, so it's gonna be plus 1, and that is one carbon to carry a positive charge here. Okay, so the positive charge here refers to the formation of the electrophile. So now our benzene, which acting as the nucleophile, gonna attack the electrophile, and this gonna causes the attachment of benzene with C double bond OR here. Okay, and as usual, we're gonna move our electron to show the resonance structure, and we're gonna enclose it with bracket and show it as the arenium ion. Okay, and now we're gonna draw the last structure again for step number 3, which is deprotonation, pembuangan proton, which is we can take the AlCl3 minus that we have formed in step 1, and we're gonna use this to attack. We're gonna use this to give extra electron to chlorine, and the extra electron from the chlorine will be used to abstract ataupun deprotonate hydrogen. Kita buang hydrogen tadi, and this will form a carbon-carbon double bond on the benzene. So now we're gonna produce our product, which is carbon-carbon with benzene attached with the acyl group here. So R ini boleh jadi apa-apa lah, boleh jadi CH3 dalam kes tersebut. Tapi kalau dalam soalan it gonna be CH2CH3, then you just change your R according to the question. Okay, and AlCl3 gonna be produced again. Alright, so now you have learned 4 types of the electrophilic aromatic substitution, which is the halogenation, nitration, Friedel alkylation dengan Friedel acylation. Okay, so now we're going to focus on the oxidation, where dia tidak berlaku dekat benzene. Okay, dia tidak berlaku dekat benzene, tetapi dia berlaku dekat side chain of the benzene. Misal kata dekat R group tadi tu. Okay, so misal kata dekat Friedel alkylation, you're gonna attach with CH3. So oxidation will happen here, dekat side chain, not in the benzene ring. Okay, so it happens at alkyl benzene with a benzylic hydrogen. So we're gonna look into that. For oxidation, we're going to have the reagent of acidified KMnO4 or the sodium dichromate. And the condition here, we need hot with hot condition, which means that it needs heat and or can be represented with a triangle here. So the product that we're going to form is the benzoic acid. Okay, so maksud benzylic hydrogen is the one here. So your attachment, your here must contain H. Same goes to this carbon here. The carbon attached to the benzene must have H in order for the reaction to occur. Same goes to here. We still have the H. So these are known as the benzylic hydrogen. Okay. So when they have a benzylic hydrogen, you can undergo oxidation, and for the observation, you can look into here. So if you react with hot KMnO4 in order to undergo oxidation for the alkyl benzene, what you're gonna get is the purple color of KMnO4 turns colorless. Maksudnya oxidation tadi dah berlaku. Or you can use hot K2Cr2O7 at acidic condition, or you can use hot sodium dichromate at acidic condition. So if oxidation happens, you can see that the orange color of the chromate ion will be changed into green. So these two observations you have to know and memorize if this is the first time for you. Okay, so now let us look into example so that you can see it better. Okay, so alkyl group akan undergo, misal kata ini adalah benzene group, benzene ring, dan dia attach kepada alkyl group. So ini adalah toluene, then it gonna react with the KMnO4, which is the oxidizing agent, reacting with acidic condition with applied heat. So what gonna happen here? The CH3 here gonna be forming the carboxylic acid. Okay, or this condition here is known as the benzoic acid. At the same time, for the benzene ring that attach with two alkyl group, which is CH3 and CH3, it can this is known as the isopropyl toluene, and it can also react with the oxidizing agent under condition of acidic and heat in order to form the dicarboxylic acid. Okay, pasal kita ada dua group of carboxylic group, and dicarboxylic acid going to be the parent name, and this refers to the benzene dicarboxylic acid. Okay, dan macam saya kata, in order for the oxidation to occur, we need to have the hydrogen. Okay, so the carbon that attached to the bromine must contain the hydrogen. Then only oxidation can occur in order to produce the benzoic acid. Same goes to here. Bila this benzene attached with the carbon and it has hydrogen, oxidation can occur in order to form carboxylic acid. Same goes to here. This carbon here will have hydrogen. Okay, so when it has hydrogen, it can be formed into carboxylic acid. Okay, dia tidak kisah how long the carbon chain is. So in this case, if I were to expand the structure, I will have CH3 and CH3. Okay, and H here. However, even though I have more carbon chain here in comparison to this one, the product that I form on this side will going to be the same. So this is what is meant by this statement here. Alkyl group, regardless their chain length, tidak kisah panjang mana sekalipun, bila dia ada benzylic hydrogen, it gonna be formed being a carboxyl group. Okay, without a benzylic hydrogen, they are inert to oxidation. They will not undergo oxidation. Okay, so you need to know the term inert here, because in some exam they will use the term inert. So inert here means that it is not reactive and it will not undergo oxidation. So misal kata if we have the benzene here, okay, so this carbon will attach with CH3, CH3 and CH3, and this carbon going to be attached with the carbon of the benzene. However, it does not have any hydrogen attached to this carbon because it attached with the alkyl group, attached with the alkyl group, attached with the alkyl group. So on this side, no benzylic hydrogen. Tapi kalau untuk side ni, if I were to expand, I will get H, H, and H. So I know that the carbon that attached to the carbon of the benzene will have the hydrogen. So ini ada benzylic hydrogen. Okay, so you can see here at this side they can react in order to form carboxylic acid, but on this side they cannot do so. Okay, so this side akan form carboxylic acid, but for this side they are not reactive because it does not have benzylic hydrogen. Okay, now we are still looking at the side chain, which is the alkyl benzene. So masih berlaku dekat tepi benzene, bukannya dalam benzene tersebut. So for example, when we react with the halogen of bromine or chlorine, this is known as the halogenation process. So for this reaction to occur, we need to do that in the presence of the UV light, and the reaction will be named as the free radical substitution, similar to the one that we have learned in the alkane, yang mana ada initiation step, propagation step, and termination step. Okay, so the step is similar, and I will not go it again, so you can refer back to your alkane chapter. Alright, so at this part, remember that bila ada reactant, we're going to put it on the left hand side. The condition, we're going to put it on top of the arrow and also below the arrow. Okay, same goes in the previous slide. KMnO4 dekat reactant side. Okay, and also similar to the previous slide here, where acyl group is going to be placed at the reactant side. Kena pluskan dahulu baru reactant. Okay, so that's just the technical ways of writing the reaction equation. Okay, I think that's all for today's video. Dan ini adalah dia punya summary of what I've talked just now. We have looked into the halogenation, we have talked about nitration, we have talked about Friedel alkylation yang mana kita attach R group. So nama dia alkyl group. And we also talk about Friedel acylation yang mana kita tambah adalah C double bond OR. So dia akan tambah C double bond OR kat sini. And dekat ini adalah reaction 1, 2, 3 dan 4. And for the side chain alkane here, it can undergo oxidation, which is number 5, and it can undergo halogenation in the presence of UV. For the oxidation to occur, it need to have a benzylic hydrogen. Okay, so these are the summary for the reaction in the for the benzene topic. So we have 4 important steps here, which is refers to the electrophilic aromatic substitution. Alright, so I think that's all for today's video. See you again some other time. Bye.